Now, of course, these meteors coming into the atmosphere come from various sources. We've heard about cometary origin, and we've just seen an unknown origin for the Geminids, perhaps. But what are these dust grains made of? To actually find that out, we need to carry out meteor spectroscopy, which is, in other words, obtaining the spectra of the meteoroids as they burn up in the atmosphere. And this is a very skilled task. And we are very, very fortunate in this country that we have one of the leading experts in meteor spectroscopy, someone who has perfected the observing techniques over many, many years and has obtained some truly remarkable spectra of meteors in the atmosphere and fireballs. So I'd like to introduce you to Dr. Bill Ward from Kilwinning, who, as I say, has truly perfected the art of meteor spectroscopy. Bill.
Thank you. Can everybody hear me? I don't know. Can everybody hear me okay? Oh yeah, I can hear the system now. I moved it slightly. Anyway, thanks, John. This is with Alec. Are you talking about somebody else? What I'm going to talk about today is in sort of three parts. One is a sort of introduction for people who might not be so familiar. The second is the sort of results I've had over the past couple of years. And then the last part, I'll be looking at some speculative work for the future and also some mention of the Geminids, because there are many myths about the Geminids. So, as probably everybody in here is aware, spectroscopy is the key element, the key tool we have to understand physical phenomena. I mean, it's used in every single branch of science. The decomposition of the light into its original constituents allows us to analyse what is actually there. Meteor spectroscopy does present some unique challenges, and I'll mention some of those as we go. And it is a world of compromises, because as I've found that you cannot improve one aspect without degrading another. And there's also a few landmines that you need to watch out for as we go along. So, just as I said, a quick introduction. Spectra basically break down into three different types depending on the source and the environment in which it's occurring. We have thermal spectra coming from the radiation itself. If the light then passes through any medium, we can have emission from the radiation stimulated as it goes through that medium, and then we can have absorption from light observed through whatever that medium may be. These are examples of your typical laboratory type spectra. I don't know if you remember your school days, you're looking through a little telescope, prism and a slit. And what these lines actually are individual images of the slit that you look through, and they're just refracted by they're refracted by the prism depending on the wavelength, so they tend to spread out. That's how these things actually work. So these are all kind of common gases: hydrogen, helium, oxygen, etc. Now, if you have a relatively pure sample, that's quite easy. But what often happens is they all compress together, and that's what we actually have. Now, this is a result I got towards the end of last year, and this is currently the most detailed spectra of a meteor ever captured. The majority of these lines are iron. There is some tungsten, some chrome. There's sodium that just squeaked in there. So trying to decipher that code actually takes quite a bit of effort. And as I say, there are issues with that. But once you get your head around the basic ideas, you see half a dozen of them, and all of a sudden you become intimately familiar with the patterns. It's something that humans are really good at. You start to see the main features, you start to see the patterns, and then you can almost immediately start to identify the groups of lines, the spacings of the lines, how it all hangs together. But trying to measure something like that can be quite complex. So, fun fact number one. Meteor spectra, by their very nature, now you have to remember what's happening. This little rock is travelling along, minding its own business, runs at the top of the atmosphere. So it's in a gaseous medium. Through friction, it begins to heat. It then melts or fragments or shatters or whatever. So it's actually a combination of three fundamental phenomena that we saw in the other slide. So what we have is, if you look at this bit of the spectra, These are the emission lines coming from the meteoroid itself. If you look at this bit of the spectra, you can actually fit a black body curve, so that's a thermal component of the spectrum. And there's just a tiny little dark line on there, and that is an absorption feature, and that's because between us and the meteor, there's a column depth of the atmosphere, and that is stuffed with oxygen, nitrogen, water vapor, and it actually absorbs some of the light. So meteor spectra are actually one of the few phenomena where you see all three types of spectra in the one go. And fun fact number 2 is, hang on a second, Starlink. I despise Starlink. Starlink are a real problem for meteor observers. The software can filter a lot of it out, but it can't deal with everything. And I actually put a comment on Twitter that Starlink satellites were the new vermin of the sky, replacing the asteroids in the 1820s, and I got a thumbs up from Elon Musk himself. So, there we go. Okay, so back to the practicalities. These are just the terms that I have evolved myself just when I'm describing systems to other people who might be thinking about setting up this kind of operation. Shorter focal lengths, wide field of view, longer focal lengths, narrow field of view. The gratings that actually do the dispersion. The number of grooves per millimetre dictates how much the light is actually spread. So the lower line count, the sort of 300, 200, 100s that you can buy, they tend to give you nice bright spectra, but relatively low dispersion. Higher line count, greater dispersion, but less light to play with. What that means in practicality is that if you have a nice wide field of view, you see lots of sky, but it tends to be a tiny, tiny aperture. So your limiting magnitude is quite poor. So you will only really see the brightest meteors. And that's okay, we'll mention that in a bit. If you want to look at more detailed images, like I do, I tend to use longer focal length lenses, but they tend to have a narrower field of view, but they tend to be physically bigger. So you can actually see a fainter magnitude, and when you're trying to get as much light out of the sky as possible, that's the way you need to go. There are 2 ways to do the dispersion. One is to use a prism, and I remember there's a picture in Neil Bowen's book with the prism held on to the camera lens, cobbled together by a sort of holder, cardboard and plywood and all this kind of stuff, and I've tried to do that, and it's just really awkward. But prisms have the advantage that a single spectrum is produced. So all of the light from the meteor traveling through the prism disperses into one spectrum. So efficiency-wise, prisms are actually the better option, but the dispersion through a prism is not linear. So it makes measuring the spectrum quite difficult. And yeah, it's bulky and awkward to put. So yeah, you try it and you go, no. And then you move over to diffraction gratings. Now, the efficiency is lower by the very way they work, but they can be blazed. Now, what that term means is that the actual profile on the grating surface, the way the grooves are cut into the glass, can be adjusted so it's not exactly an equilateral triangle. It can be offset a little bit. And what that does is it steers the light in a preferential direction simply because of the laws of diffraction, the laws of optics through the glass. Other problem, multiple orders are produced. I think I've got a graphic after this. What that means is that when the light is passing through the grating, the spectrum breaks up into multiple versions of the spectrum. You have the single image, the 0 order, first order, second order, third order. But the more you go off axis, the more these images overlap. Trying to decipher that is also a bit of a nightmare. However, they are flat, usually square. You can fit them into a lens holder and screw it on to the thread, dead easy. That's the way to go. So this is what I mean by the order overlap. If you can imagine, this is the original beam of light. This is the first order. Second order, the dispersion is twice as much as the first order, but you can see here, and since we've got 2 screens, you can see over here, the spectrums are beginning to overlap, and it actually gets progressively worse the higher order you go to. So you need to be very, very wary of that. And I've got a few images with little marks on it just to highlight that as we get to it. But order overlap is an issue. And I have seen papers in genuine peer-reviewed journals where this order overlap has not been taken into account, and the authors have actually tried to identify really quite obscure lines, when if you actually measure the wavelength, what it is order overlap from the previous spectrum. It's quite surprising. So, end of the day, depending on what you want to do, you need to use a bit of judgment. So if you're setting up a basic system, most people start with a kind of wide field. The GMN systems they have different. I'm not entirely sure about the optics, but they're a kind of wider field system. But as I've alluded to, there are issues with the magnitude. But if you're looking for fireballs, that doesn't really matter because it's going to be bright enough to be seen. But if you're trying to eke out very, very faint lines in a spectrum, then you need to go for fast lenses, big lenses, but they inevitably are narrower field of view. So either live with catching fewer spectra or you use multiple systems and try and cover as much sky as you can. And certainly over the past 10 or so years, I've tried to add to stuff as I've came across it in eBay. But there is always this compromise that when you gain one parameter, you lose in another. So, the image reduction. So this is what you ultimately end with. Like your little camera, this is one of my Watex. The lens, gratings on the front. I sit it in a little empty, you can order empty film holders. You actually use a lens cap to hold the grating in place, and then you can rotate it. And it's really convenient because sometimes when you're looking at particular shivers, you want to orientate it so the meteor falls at a preferential angle to the dispersion, and you get better results. So this is the kind of thing you get. And if you notice these lines here, this is actually magnesium, sodium, some oxygen lines. These are near-infrared lines. But this little line up here, now if you didn't know what I'm telling, you might think that is part of the spectrum, but that line is actually the same as that line. And that's one of these examples of an order overlap. You need to be wary of where your spectrum is actually running from and to. You then do a bit of adjustment with image processing software, orientate it so that you can then crop off any of the pesky order overlaps. You also need to be wary of stars because the way you process these images is you basically bin vertically, so you sum up the counts of that line into one line at the bottom, as it were, and that's what you extract the spectrum from. So stars can be a bit of a problem, and again, you need to be wary of that. How do you get to the line measurement? And again, this is a bit of a black art as well. This is a small mercury calibration lamp that I use. And what you need to do is when you're starting, it's always good to get an idea of how many nanometers per pixel your system is spreading the light. That's actually not quite the same as what you get in genuine astronomical spectrographs who measure nanometers per unit angle on it. But it's easier to get your head around just going for the nanometers per pixel on whatever system you have. And then if you know the wavelengths, you can then just determine so many nanometers per pixel to here, so many nanometers per pixel to there. And if there's unusual lines that come in between here, you can use a bit of mathematics, very simple addition, subtraction, and you can determine what these unknown lines are. So it's quite straightforward once you get a sort of handle on the way the individual systems work. So then you graph the spectra. Again, these are the lines just from reference spectra. To be radiometrically correct, you generally divide through by a known flux standard. I tend to use Vega, and that produces a relative radiometric correction. It's not absolute because you don't actually know the luminosity, and that's the problem with all meteor observing. You do not know beforehand what it is the sky is going to throw at you. So the best you can do is basically a relative measurement against something else. But that is a radiometrically corrected graph. And then what I tend to do is what we'll see a lot of in the next section. is you can just use some image processing software to colorize the spectrum, and I love these. I think these have an immediacy that is far superior to a graph when you're presenting this work. So you see the kind of greeny magnesium, the yellow sodium. This is an oxygen line, this is oxygen nitrogen, and these are all oxygen and nitrogen lines in the near infrared. So that goes from about 500 nanometers up to about 890 nanometers there. So, to get to the good stuff now. What I've discovered as well over the years is that apart from the primary compositional information a spectra gives, there is a whole host of what I call secondary information, which the spectrum is telling you, but it's not necessarily about the spectrum or the composition of the meteor itself. And this is a good example. This was just a couple of months back. This star here is this star here. These are both Deneb. These took place within about 20 minutes of each other. If you were lying, as Alec had his recliner, observing the sky, these would appear as two lovely, bright meteors. And you'd note it down, magnitude, position, whatever. But they basically look the same. But this is it's actually a really good example of how they are not the same. Because when you look at the spectra, they are completely different. So that's the first one, and this is the second one. And unfortunately, there's a lot of conflating issues here, so I'm going to have to ask you to jump back and forth between slides. If you just remember, see that line there? That's for people over on this side, that line there, because we're going to get into the realm of quantum mechanics. This is a rocky, stony, cometary type particle, and this is pure iron. Iron, and there's probably a couple of nickel lines in there as well, but it's basically an iron. So they are both the same, but they are completely different, and you would not be able to tell that without spectroscopic analysis. Oops. So that's the rocky one, and that is the iron one. Again, you can see the groupings. The iron appears in some percentage in almost every single spectra. It's inherent in the mineralization. It's just the same stuff that's under our feet. But the pure iron ones don't have the sodium, they don't have the magnesium, they don't have a lot of the silicons and what have you as well. So that's the only way you can tell what the particle is made of. And that's actually quite a good example. They happened, I'm saying, within 20 minutes of each other. So another example of the secondary is it or isn't it? This is the Perseids 2022. Now, I didn't see that one, but I did see that one. And again, you'd be on your recliner, taking your notes, and as far as you could see, both of those were perfectly normal Perseids. Lovely, -2, -3, almost fireball bright. But they're not. The first one has this little line I identified earlier, for the people on this side, that one there. The second one doesn't. Now that means they are dynamically different. This line is from a forbidden transition of oxygen. It means as the atmosphere is excited. Now we have to remember that a meteor, when you're looking at a meteor, you get the impression it's zipping across the sky. But not only is it zipping across the sky, it's falling. It's going from a low-density environment to a high-density environment. And that line there only occurs when the mean free path of the atmosphere around it is sufficiently large that an excited oxygen atom doesn't bump into any other atom within 0.7 of a second. If it does, it's collisionally robbed of energy, as they say, and it doesn't emit above a particular height. It can stay excited for long enough to then give off that photon. So that one's a Perseid, 60 kilometers per second. This one isn't, because there's no oxygen. So that was burning up much lower down in the atmosphere, so it's much slower. So we can say that, so your sheet would say 2 Perseids, but you actually only saw 1 Perseid and an interloper. I've also put a little mark there, a little mark there. Now, this is an example of order overlap again. You could just about squeeze in one of the lines to say it was an oxygen line, but not that one. But what that actually is these two lines here. So that's the first order image of the calcium lines in the near ultraviolet, and those two are actually the second order overlap. So you need to be really careful when you're interpreting your spectra, what you see on the image and how you actually put it onto a graph or an image to show what you've actually recorded. So you need to be very, very wary of order overlap when you get into the kind of higher resolution end. So spectrum classifications. This is another thing that I discovered, and I can't find any reference to it, so I think this is quite a significant discovery. That I was at an international Meteor conference a number of years ago presenting a poster using some of these images, actually. And of course, somebody ambles up at the poster session and says, what do you call this? And I have no idea. I really didn't know. You can use all sort of long-winded descriptions about its oxygen and sodium and magnesium, but there's no succinct way to actually determine what it was. Now, you're probably all familiar with stellar spectrum classifications, O, B, K, G, F, R, etc., etc. Now, I had in the back of my mind it would be something like that, and it was, but not the way I thought. So, from nearly 1,300 spectra that I had collected myself over about a decade, what I discovered was that there are actually only 3 basic types of meteoroid particle that are entering our atmosphere. There was in the 1950s, just prior to the International Geophysical Year, the Russians had it tagged as there being basically 2 types, rocky and iron. Running up and after the IGY, Peter Millman from the Canadian, he came up with a new scheme, which was W, X, Y, and Z, but it wasn't in that order, and I don't know why he never had it actually in alphabetical order, but anyway. It was based on if you saw some set of lines, it meant it was this. If you didn't see some set of lines, it meant it was that. That's because no complete spectra existed even then. There about 300 spectra had been gathered from the early 60s to the first spectrum in 1897. And in 10 years, I've got 1,300. So, I mean, things have accelerated dramatically across the whole field. But there are just 3 basic types I can see. This type A, what I call a type A, is this rocky. And again, it's very characteristic once you start to see the patterns. You get groups of infrared lines. You have magnesium, sodium, and you have a group of iron lines. You have the type B that are pure iron. There's nickel and some chrome, some tungsten, some vanadium, but you only see that when you get really high resolution spectra, sometimes in the second order. But they're the 2 kind of principal types. But what turned up in the data was this type, what I call type C. Now, Alec has actually recorded one. He sent me a picture saying what's in this spectrum. It was one of these. There have been another couple I've seen in other articles, but not called that. But they stand out on their own. They are definitely a strange mineral with just iron lines and this extremely bright sodium line. And I have no idea what it is, but they are there as a separate entity in the data. I've recorded about 20 of them over the past couple of years. So they're real. So it gives you this third category. And just to cover all the bases, I said there's a type X just for anything else that some comes along and creeps in. So I think that's quite significant that we only have these three major types.
5 minutes, Bill.
Okie dokie. And again, very recently, just this year now, a possible type A subgroup. This was classed as a Leonid, but I'm not sure. And again, it goes back to the dynamics of the spectrum. The Leonids are very fast, 70 kilometers per second. That normally gives you a really bright, in fact, they call it the orange band around that, and it's caused by the stimulation of nitrogen molecules in the atmosphere. This doesn't have it, but what it does have is this group of silicon lines and some longer wavelength iron lines, and I've seen 2 or 3 of these now, so it looks as if they're definitely the rocky type. There's the atmospheric oxygen, they have sodium, so it is a rocky type, but they have a unique set of lines in there, so there's definitely something going on, so I think that might be a kind of type A, and in brackets, something that's coming along. quick look at the sodium. I was approached last year to provide some graphics for Sky and Telescope, and the author said the spectrums I had sent him were incorrect because he said 80% are sodium-free. That is just not true. This is from 2024 on its own. Sodium, 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 sodium. 2017, there was a paper written by Galina Ryabova, Jürgen Rentel of the IMO, saying that the Earth was possibly going to encounter particular streams from the Geminids. So Pax Mageia heads off to Tenerife, and I have about 20 spectra. And again, with time, I could bore you to tears with them all, but they all show sodium, and some of them are so bright in sodium. It's actually quite similar to this one. They actually have a sodium tail. The sodium is that strong. So I don't know whether it is an interpretation of the data, because the author would not send me his spectra. Take that what you will. Or whether it's just the language. What do we mean by sodium-free? I mean, volatility and the value of the level, I don't know. I noticed at this year's Professional Meteoroids Conference there was a paper presented saying the annual variability. I could buy into that because it gives you some wiggle room on what's happening, but to say that 80% are sodium-free, yeah, I think that's a myth, a complete myth. Yep, couple of minutes. So, right up to date, 2 weeks ago, at the last IMC, I had an incredibly detailed conversation with one of my Japanese friends, Nagatoshi Nogami, and he's developing an idea to explain the very long duration persistent trains. Some of the chemistry is quite well established, but trains that last 15, 20 minutes have to be self-luminant for that time. They have to display the luminance for that time, and that's very difficult to explain. So he's diving into the quantum mechanical world now, looking at the excited and trapped states of what are called excitons, which are electron-hole pairs that happen across the valence and conduction band, and this is going to be a whole lecture on its own. But I played a hunch, and I thought, what have I got that's like I could use as an analogue to show how that might work. So I rummaged around in our geology store, and I hope this plays, because in principle, this should only happen in crystal structures, not amorphous structures. The trouble is, if something melts, it tends to become amorphous. So we'll see if this... So this is 2 big chunks of obsidian that I am rubbing together. Now, that's not sparks. These aren't sparks. This is actually light coming from within the body of the material. And that's coming from the impurities caused by the iron and sodium that's within the obsidian. And it just so happens that pretty much all of the lines there, magnesium was missing, but you know, it was an analogue, it was a hunch. These all appear in meteor spectra. So it might very well be onto something. When we did an EDX with the electron microscope, we got all the concentrations and what the kind of mineralizations could be, and again, they're all entirely reasonable. So what might be happening is that in some way, when the meteor enters the Earth's atmosphere, it heats up, the electrons in the body of the remaining droplets are actually put into an excited state, trapped in particularly the silica material, and then they themselves give off light over an extended period of time. Bit theoretical, and one of the things we need to do is get a spectrum of a long duration train, and that is not easy because they're faint, diffuse. It's something that we'll need to look at, but it shows you things are still under development in meteors. You know, it's not all done and dusted, and there's still a lot to do. So with that, and I think that's me on time, I will just say thank you for listening.
Well, you're seeing some really top-class meteor spectroscopy there. That really is superb work. Any questions for Bill?
That's fascinating, Bill, right? See the spectra you showed that was all kind of monochrome. Do you have that in colour?
No, I use monochrome cameras because you don't have the colour matrix in the front, because that cuts out some of the light between the Bayer matrix and also limits the UV and IR ends of the spectrum.
But looking, this will sound really daft to you, but I love stuff like this. It looked like a tartan, you know, like in my kilt. It looked like a tartan, you know. And if we have that in colour, we could maybe have a meteor tartan.
It's maybe not a bad idea.
Any other questions for Bill? Can I just make one observation, Bill?
Yep.
The observations of 3,200 Phython that showed this sodium tail seems pretty obvious that sodium is going to be part of Geminid meteoroids? Or is that too simplistic? It seems to me fairly obvious now.
Exactly, and that's
all
why
fits in.
When I spoke to the sub-ed on Sky and Telescope, and I said, well, listen, can you put me in touch with the guy? And he just sent me an email saying, no, I'm sorry, you're wrong. And I'm going, well, I can send you my pictures if you want. I mean, I've got spectra going back to 2012. That's 13 years, 4 or 5 good Geminid peaks. And every single spectra, it's variable. And as I'm saying, that's how the last paper made a bit more sense. But sodium is in every single one of them. So whatever the language difference is, whatever the interpretation is, 80% are not sodium-free. Absolutely not.
Absolutely. Thank you.
A quick question on that. So, and this is probably because I'm not paying too much attention to this, but we know that the Geminids come from something which is not a normal comet, whereas most other meteors do. So when you see your spectra, are Geminid meteors qualitatively different in their spectra?
No.
No, they're not. Right.
Mine just biting into the coffee time a little bit. There we go. See, that there, that's, I'm saying, 2024, that was the, where's my pointer? I prefer this one, because I end up doing it backwards. That one there, iron group, magnesium, iron group, sodium, oxygen, atmospheric lines, okay? Entirely, almost identical, but that's a completely different shower, completely different, it was a sporadic iron, magnesium, sodium, oxygen, infrared group. So they are the same. They are absolutely the same.
Okay.
So they are rocky. They're definitely rocky, but they've got sodium. So it's not as if the sodium is being completely volatilized and disappeared, which I think was the idea for a while because it was very close to the sun and it would come out a solid solution and disappear into this tail. But the particles are still carrying enough sodium to come up.
Basically, that idea doesn't work then, essentially.
Yep.
Yeah, they look the same.
Absolutely.
Interesting.
And that really does show the value of this work. When you can think of all those years up to when Peter Millman did his classification, they had just a couple of hundred spectra. Now Bill on his own has got 1,300 plus. It shows the value of this work. Please return your thanks again to Bill Ward.
Thank you.
Tea time.
Yeah, so tea time, folks, and we're back at 1:45.